voice quite well in the back as well. I'm sorry, I come up with the flu this morning. Literally woke up with my head full of snot, and I'm doped up on ibuprofen talking to you today. So let's hope you know, you can understand. And if my voice disappears during the talk, apologies in advance. So my name is Ilkka Turunen, and I'm a solutions architect for a company called Sonatype. So in my job, I work with a lot of different companies across the world, especially here in EMEA and Asia, helping them look at their software development pipelines and introduce what we call software supply chain principles into there. Today's talk really for me is about bringing kind of like the top tips of what we see in the trenches and really show you what can be done in order to facilitate security as a part of the software development process instead of actually being something that halts the process. So my background isn't security, and I would never have characterized myself as a security guy. So just to kind of get over with the credibility slide and the credibility aspect of who I am. I've done many different things. I've ran my own startup for a while that was developing products in application lifecycle management. We did some interesting meta distributions of Debian and Ubuntu Linux in terms of kind of a pick-it-your-own tool set. I've worked as a CI/CD pipeline consultant for a number of years in London, helping some companies, large and small, the largest being a Fortune 10 company with a massive office in a really financial part of London, helping them figure out how they're going to tackle this sort of cloud computing type of thing that was really new to them last year. Everybody else has been talking about it for quite some while. And finally, recently I've been working with Sonatype to really help customers figure out how to introduce continuous delivery and how to think about software supply chains as a part of it. One thing I'd never, like I said, one thing I'd never call myself would really be a security guy. So I definitely am not a security professional, as some of you guys are probably much more into it. So one of the things that I wanted to do in order to kind of prove the point is I wanted to have a practical demo of a CVE that was released last year in order to kind of start this talk off. How many of you recognize that code? Not very many. Good. So it's quite simple. CVE, that particular CVE has to deal with something we call Jenkins. Jenkins, as we know, is a commonly used CI and CD pipeline. Here's seen chugging along nicely in my application. This isn't chugging along in my software development environment. I've got some builds running here, and let's imagine my imaginary company is chugging along nicely. Well, what happened last year in the end of November, some of you might have seen this, was that there was a company called Foxglove Security that came out with a interesting exploit that allowed people to compromise a lot of different applications, Jenkins being one of them. Now, to demonstrate you how complicated this vulnerability exploit is, it's here. It's 41 lines. Well, you can't really see it. It's the resolution isn't exactly stellar, is it? But it's 41 lines of code. So here we go, 41 lines of code. Now, what we can do with this is we can basically take this code and send a payload to Jenkins. And what we can do is basically take that 40 lines of code, point it to the server that's running on my local machine right here, and send a payload that does something. Well, it uses something called the remote CLI capability within Jenkins in order to send a piece of malicious code. And what that does is simply allows me to write a file in my temp directory, here seen under the pwned text. So as you can see, not a very complicated exploit to leverage at all, and even someone like myself who hasn't got a background in security at all could take this line of code and learn how to use it within about 5 minutes of figuring it out. And this is something that's publicly available on the internet, went around everybody's inboxes last year, and is very, very readily available for use. Well, to the commendation of the Jenkins project itself, they released the mitigation on the day this article went out. So on that very day when this exploit that came out, or this vulnerability came out for this particular part of the Jenkins functionality, their CTO himself committed a patch into their version control system that you can publicly look at GitHub. They released a fixed version a few days later with a workaround being circulated to all customers on the day, right? So this much you guys probably already know. You know, this isn't something that is new or anything special in the world of security. You know, exploits like this come all the time, and occurrences of these exploits happen at any given point. So this much you guys probably already know, you know, from the back of your hands and from the bottom of your hearts. It's probably like preaching to the choir, right? So what's interesting here is that I then asked the question, okay, well, obviously, you know, we're half a year in now. We're, you know, half a year later. Everything should be peachy. Everybody should be running on a patched version right now of this service, because Jenkins obviously is quite a popular open source tool to use in order to facilitate continuous integration. So I went to somewhere called Sodan. Sodan is a search engine on the internet that was originally actually developed to allow developers to search for open Internet of Things applications. And what I just did there was I went in and I asked, how many Jenkins instances can I find on the internet running on the default port, publicly available without any firewalling? And the answer to that, this is a dashboard of that search, is, again, we're not seeing very much. Here we go. The answer to that was, in that, you know, 5-minute Google that I did using this sort of search engine, I managed to find 13,000 different running Jenkins instances on the internet. Well, you know, no big deal. I mean, obviously, they might be running on the public internet without, you know, some of them without any access control, but that doesn't mean that they haven't been patched, right? That doesn't mean that they haven't been fixed in this version. Well, I took an export of that data. Unfortunately, you can only take it in chunks of 10,000, otherwise it will start costing you. So I looked at the first 10,000 series of those 13,000. And what I found out, basically to conclude this numbers, is that 32%, 33% of those particular servers had not yet been patched. So 33% of the publicly available servers had not had that patch. So the question becomes, why is it that after 6 months of, you know, perfectly clear messaging, perfectly clear advisories, haven't these sorts of issues been patched? Now, this isn't necessarily uniquely a Jenkins issue either. It's just something that's a very easy and tangible example to illustrate this sort of vulnerability. Well, the question is, why are those one third of these instances still being left unpatched? And second of all, what is the real cause of this issue? Well, that's where my company's unique point of view actually comes into play. So this vulnerability, this exploit, so easily run and so easily, you know, allowing me to, you know, write files on a file system, is actually caused by a third-party component that is used as a dependency in the Jenkins application. It does not come from their own code at all. In fact, it is caused by a library called Commons Collections, which is a part of their dependency chain inside of their own dependency management code chain. So this Commons Collections component, this article was titled like this because this component was found in all of these different applications. And this actually is a surprisingly large issuer and cause of vulnerabilities and of exploits in applications. So these third-party components actually comprise a surprisingly large amount of the code base of your final application. My company did a little bit of analysis on something called the Maven Central Repository. The Maven Central Repository is the largest collection of open source components that is available on the internet. It has about 1 million different components that developers can download in order to use as a part of their software delivery or software construction process. And what we did was we asked some of the users there to analyze their applications and tell us how many components did actually end up in a final compiled application. And the final numbers were an average application, an average enterprise application from an N of about 2,100. There is a link to the report where you can see these numbers at the end of this. Had about 106 unique components built into there. And out of these 106 unique components, 24 had some sort of known vulnerability associated into it. Also, there aren't just evil hackers out there to get companies. There were also some restricted licenses. So we then asked the question, what does the average download cycle of a Maven Central user look like? So when a company downloads components from this massive open source library in order to build their applications, Maven being the most used build tool in the Java world, we came up to the numbers that said that the average customer will end up downloading about 240,000 components a year. So the average company will end up downloading about 240,000 components a year, and out of those 240K, about 15,000 of them contained some sort of known vulnerability inside of them. That adds up to about 6%. And now, that means that in every application that gets sorted, some sort of a known vulnerability that gets compiled, some sort of known vulnerability is already bundled in there, 6% of the time. But what's really, really scary in this number is that out of all of the vulnerabilities that were downloaded, so these 15,000 vulnerable components, about half of them, just over half of them, had a vulnerability that was older than 2 years. So that vulnerability was actually disclosed over 2 years ago that got bundled into that application. So the question is, why are we allowing these sorts of things to go into our applications? And why are we allowing these sorts of things to be downloaded? I mean, obviously, no one downloads these because they want to download these bad components or bad vulnerabilities. So why are they still making their way into there? Well, one explanation is that if we look at the vulnerabilities in the MITRE database, the CVE database, where we put all of these things, that Jenkins vulnerability was disclosed there in November 2015 as a part of the Commons Collections exploits that themselves were published in AppSec California earlier on. It turns out that for every one vulnerability that gets a lot of publicity and gets the industry moving and actually patching issues and patching things, there were about 62 other critical vulnerabilities, so meaning CVSS score of 7 or higher up until 9, and 19 critical vulnerabilities that were also disclosed in the MITRE database. So not only did we discover a single vulnerability, there were actually 81 other vulnerabilities that were also discovered at the very same time of equal or more severe exploitability, and yet we don't hear about these. So one of the explanations here is also when it doesn't, I mean, obviously you guys know, but when it doesn't have a logo and a nice website with a bleeding heart, it very often emits our attention, and that creates a false sense of security. And that doesn't mean they aren't there. And if we look at the Verizon Data Breach report from 2015, we've actually found out that 10 CVEs amounted to 97% of all of the known attacks to Verizon in 2014. And if you look at the CVE codes here, the oldest one of them is 1999, and most of them come from somewhere in early noughties. So in 2014, all of the known web attacks, 97% of them were done with 10-year-old or older exploits that were publicly available on the internet, publicly accessible, and completely publicly sourceable into the applications. So question is, why is it that even though we should be aware of these vulnerabilities, and we obviously should be aware of how to mitigate these vulnerabilities. We obviously aren't, right? Most of these are Microsoft-related, Microsoft and Windows-related problems, but one of them is Poodle. So Poodle, for example, was exploited very, very much. And it isn't uniquely an application-level problem either. So when we look at applications, these problems obviously do exist. But there was another company called Banyan Ops that did some research about Docker containers. They looked at the Docker hub and looked at all of the containers hosted in there and asked how many of them have, you know, some sort of known security vulnerability. And they found out that out of all of the containers over when they did their analysis last year, 36% of them had a high known security vulnerability built into there. Well, okay, fair enough. Not all containers there are, you know, even updated anymore. They're just retained for backwards compatibility purposes. So if we just look at the containers that were published in 2015 alone, we still found out that 40% of those containers contain some sort of known high vulnerability. Finally, what we saw, even if you look at just the latest images that were published into that Docker hub, we found out that 23% of them had some sort of known high vulnerability. So the conclusion here is that this problem exists across the entire spectrum of the software development lifecycle, not just in applications, but also in systems and also in environments and even data centers. I call this compound risk. You know, I've been thinking about this quite a lot recently, about why is it that these sorts of risks end up making themselves into their applications. And the answer is because of something called compound risks, right? So we use some sort of quant of reusable code, like jar files or whatever packages, in order to build our applications, right? We use those and we build and bundle them into specific applications. These applications then, you know, we bundle them together, we use some third-party applications elsewhere, and we deploy them into some sort of containers and some sort of other virtual machines or Docker containers or whatever that then run those environments. And those containers then get provisioned and become information systems. Now the problem here is introducing a vulnerable bit, you know, especially when it comes from an external source at any given time of this process, will end up compromising that entire chain. So if you have something that's faulty down here, it will end up actually destroying might end up implicating this system here at the top. And the problem is build processes, bundling processes, and provisioning processes tend to also not be very transparent about what is exactly being bundled into a final application. So for example, if you run a build or a dependency make, you will notice that a lot of them tend to actually not disclose the list of, for example, what sort of transitive dependencies ended up making there. Well, I then asked myself, how, you know, there's a very old known wisdom in the industry that says, you know, fixing things earlier will make things better and will make fixing things faster, right? So fixing an issue, a vulnerability earlier on in the software development lifecycle will be faster. So I looked at the Journal of Defense Software Engineering, just found an estimate of how much faster it is to fix an issue earlier on the software development lifecycle. So if we find a problem when it's already gone into a live system, it can easily take 250 units of time in order for us to fix it. But you know, if we fix it earlier on in the development process, right here at the very early stages, it might only take 1/10 of that time. But the question is, we're using quite a lot of open source now and quite a lot of third-party components in our applications. There are now 106 of these in every single application that we end up bundling in. So the question is, it actually probably is even faster, even faster to just block these bad things from coming in the first place. So the very fastest thing that you can do in a software development cycle is actually stop these from happening in the first place. So, you know, not accepting you know, these bad components in the first place. This all sounds hopefully quite, you know, clear as day and probably very very blatantly obvious. But the question is, and it should be blatantly obvious. So the question is, how are we trying to prevent this from happening today then? Well, almost top 10 in the 2013 edition included for the first time the new point A9. A9 or using components with known vulnerabilities. So even OWASP, recognized that this sort of vulnerabilities actually exist and published some tooling in order to fix it. So this has been out there for a long time, and because that is used as a reference, many standards actually contain some sort of reference or guidance to addressing this sort of issue. Like, for example, PCI DSS has the requirement 6, PCI DSS being a standard used in the financial industry and payments industry that says in order for you to be able to process payments, first of all, you have to establish a process to identify security vulnerabilities by using a reputable outside source and then categorizing them. But most importantly, ensuring that all system components and software are protected from known vulnerabilities by installing applicable vendor-supplied security patches. Well, it seems like we're not very good at following standards. There are also other standards like the IEC standard here that deals with medical devices that also says that when we're using software of unknown pedigrees or components of unknown pedigree, things that we haven't necessarily written ourselves or things that have been shared by others, we have to establish processes in order to follow these sorts of things. But too often, in my experience from the development side, it ends up working out something like this. So this is a PCI DSS requirement checklist that is an Excel sheet, a worksheet that allows me to check boxes off and check risks off from my applications. The problem with this is too often from a development point of view, this becomes more of a checkbox exercise than an actual actionable item. So we kind of go around, we gather all the answers into this, and we say, you know what, we're compliant now. But unfortunately, compliance isn't security. And in this case, the road is always kind of paved with good intentions. So, using this sort of checklist, kind of hounding and scolding developers and asking them, are you compliant with this particular piece of legislation, can easily lead up to the outcome, in my experience, of the top 3 most critical items being checked off and everything else being addressed later on in the development life cycle, meaning maybe in 5 years' time, maybe in 15 years' time, maybe, it's been since 1999, we still haven't quite checked that list item off from there. Now, another way of combating against, these sorts of third-party dependencies is approving components in bulk. So, running some sort of, analysis on every single component individually, and then saying, okay, that's good, that's bad, that's not okay. But as an organization grows, and as I'll later show with a couple of calculations, this becomes an unstable and unscalable process. And finally, some companies I've seen have actually entirely deplugged from the internet and said, you know what, we will not allow anyone to download anything. We will write everything either in-house, or we will only, through careful consideration, bulk approve things that you can use to build your applications. And this, unfortunately, isn't things that you can do today if you're trying to, work in a continuous delivery or continuous integration fashion, because that just means that you're hindering the development process from happening. If you're trying to aim for 100 releases a day, this certainly isn't the way to go. So what can we do in order to facilitate these things as a part of the software development process instead of actually working against it? What can we do in order to facilitate this sort of actions happening? Well, I would like to introduce you to the concept of supply chains. The supply chain is a concept from the manufacturing industry that says that, for example, if we have a laptop, that laptop consists of many different parts that are used to assemble, right? A laptop has a keyboard, has a screen, has an aluminum body. Well, if you take the keyboard, that keyboard is made out of plastic. That plastic comes in granule form, it's melted down, and then formed into the keyboard that is then assembled on top of the electronics, probably assembled by some other party onto my laptop. And that plastic granulate comes from crude oil that is drilled by some other company, some other places. So all of these sort of actors collaborate and work together in order to provide, in order to create a piece of raw resource that we are using to build our final product. And that supply chain doesn't actually end there. You know, after a laptop is complete, it goes to a computer wholesaler, goes to a computer store, and then finally to a customer that buys it and uses it and, you know, puts it in here that I can then use as a part of my presentation mechanism. So this supply chain concept actually exists in the software ecosystem equally, as we saw in the last example. And we can actually leverage advice from that very same industry in a very similar way. So there's a guy called W. Edwards Deming that helped transform the manufacturing industry of Japan in the 60s. Most notably, a little car company called Toyota that he helped transform using his 14 principles of management into efficient manufacture of cars that had an advantage that lasted for decades compared to competitors. We've stolen a lot of his principles already in software. You know, lean and agile methodologies actually lean a lot into his thinking. But there are two things that we still haven't quite stolen from him as an industry. First of all, he says, cease dependence on inspection to achieve quality, and secondly, move towards a single supplier for any one item instead of buying on the basis of a price tag. So instead of, you know, just getting what seems to be the lowest friction supplier, instead what we should do is we should cease dependence on these sorts of things. And finally, we shouldn't, you know, do inspections in order to achieve quality at the end of a process. We should actually build quality as a part of the manufacturing process. So we should facilitate quality so that it actually happens as a part of the manufacturing process of, you know, cars or whatever, instead of, you know, waiting until it is done, then stopping the process and looking at it and trying to fix it. And these have had some very, very tangible benefits. And this kind of supply chain logic actually works exactly the same in software manufacturing as well. We have supply chain managers in our software, but instead they're called dependency managers or build tools or whatever. In Java, for example, here's an example of how a Maven dependency looks like. Here's an example of how Ruby gems look like, and here's an example of how in the Node.js ecosystem this similar type of mechanism ends up working out. And so dependency managers actually do exactly the same function. They source some other dependencies that you then use to manufacture your software. And this supply chain is actually surprisingly complex within the software industry specifically. There is a concept known as transitive dependencies, meaning dependencies of your dependencies. That means, you know, the suppliers of your software also use other suppliers to provide some functionality for their software. This little dust mite here in the space isn't actually just a, you know, nice illustration. It's actually a visualization of all of the components that were housed in Maven Central in the middle of last year, if I remember correctly. And all of these white dots are those components. These orange lines are their interdependencies. So dependencies of other dependencies of other dependencies. So that supply chain of software quants gets into a massively complex point. So what can we then do in order to translate those same supply chain thinking from the manufacturing industry into the software industry? Well, first of all, you have to control the amount and quality of your suppliers and the components that you use. Secondly, we have to standardize our component catalog. We have to standardize what we use instead of allowing every developer to choose their own, you know, tools. It's kind of like going to a car mechanic that has a, you know, car mechanic chain. Every shop just has a different set of tools inside of there. You know, instead, we should, you know, come up with a standard toolkit in order to limit the amount of stuff that we're downloading. Third of all, in order for us to then chalk off those, you know, 10 bad CVEs, we have to learn to leverage automated quality controls as a part of the continuous integration pipeline. And finally, we have to maintain what is known in this development industry as a bill of materials, or a list of all of the components that go into an application and their underlying components. And of course, one thing to also recognize here is that isn't something that you can just run with tooling. You have to actually take ownership and institute leadership within the development teams themselves in order for them to start using these things, because just tossing things at people will not necessarily make them use things. So let's look at each of these points really quickly and see what are some concrete actions that we can do in order to facilitate this. Well, first of all, you have to control the amount and quality of your suppliers. So how can you do that? Well, first of all, you have to ask yourself a couple of quite deep questions about what to look out for in a good supplier in the first place. Things like how often do they release? If you have a project that releases often versus a project that's released once in 10 years, that might give you a bit of an indication of the quality of the team and the ecosystem behind it. And secondly, of course, we have to look at things like how popular is this project? An Apache top-level project or a Novos project is probably more trustworthy than something coming off straight out of GitHub. Of course, we have to look at what's internally popular, what's popular inside of our own software development ecosystem, meaning our own developers, in order to standardize what's already known. Finally, of course, we have to look at things like security vulnerabilities, how fast they're actually fixed by those projects and suppliers, and of course, loads of other aspects. But the key thing here is that tooling can help facilitate these sorts of things. Things like artifact repositories might actually be a very valuable tool for you to help take a glance and actually create an audit of what is present in your application. So if you look at a basic software delivery pipeline, we've got some developers, we've got some SCM, build automation, a binary repository manager, deployment automation, and some target environments. A binary repository, what happens normally is a developer checks out some code from an SCM in order to start developing, and they also download some dependencies using these dependency managers. Using a binary repository between a third-party public repo actually can help you keep track and audit what is being downloaded. So that helps you stop, for example, the bad stuff coming in order to, or at least have a glimpse of, are we using one of the components that have these 10-year-old vulnerabilities that we've been seeing. Well, and so it allows you to really create a control point of these components. And another thing that it does, it actually helps you mitigate risks from that third party, that public repository going down. There's a well-known example in the NPM ecosystem where a Turkish developer got really angry at Node.js and the community and pulled about 273 of his own components outside of the NPM.js library. Well, what ended up happening was one of them was called LeftPad that was relied widely upon by the ecosystem of NPM developers. And that component caused thousands of builds to fail within minutes of it being pulled out. Pretty scary stuff. Well, what kind of component is this? What kind of component was so crucial that it caused all of these builds to fail, including the core of NPM itself? It was 11 lines of code that takes in a character, a string, and pad and a number, and pads the string with the character for as many times as you put the number. Right. So the guy pulled that out, and all of these builds started failing because this risk of that third-party source was not seen as a very, very large risk. But when it did happen, all of the builds started failing because of this being missing. So not only does it help you catalog things, it actually helps you mitigate some risk from there on as well. Now, a second thing, of course, is to standardize this catalog. So what can we do in order to make things better? Well, to refresh the stats, if we have 106 components in one application, very, very few companies just build one specific application. If we multiply these numbers by themselves and we assume that we also use more than one version of a single component, what we can actually see that the number of actually used components cascades very, very rapidly. So standardization is important. So we cannot allow, or we cannot let people use all of the available components out there. We have to let them. We have to actually standardize and say, here is our toolkit. Here are the few different components that we want to use in our specific application. And we have to be picky about them as well. We have to make sure that, you know, we use those same quality metrics that we spoke about in the last point, and actually also then extend that thinking into saying, should we really allow 5 different authentication libraries across our company, or should we just use one trusted version or one trusted supplier in order to provide that sort of functionality? So not only can that piece of tooling act as a catalog, a control point, it can now act as an audit trail as well and help developers make the decisions about their toolkit. Move away. And this is, for example, how that sort of standardization might look like. You might, for example, say that instead of using all of the available versions of JUnit as a part of building our applications, we only want to use, for example, one specific thing. And we can actually write tests on it. We can actually write the normal tests that run and say, unless it's a component that we want, version that is approved, you shouldn't use it. And that gets me to the largest point of the day. Leverage automation as a part of your existing workflows as a part of security. There are many different frameworks of what should happen as a part of the development pipeline and what should happen as a part of the security process. This comes from an FS-ISAC report, so the Financial Security Information Security Association, that tells, shows a singular model of software security as an assessment. And it says, for example, that, you know, you should run binary static scans, dynamic scans, pen testing, and web application testing. You can run all of this manually, but if you want to, you know, keep up with the pace of development, ideally, what you want to leverage is something that the developers do every single day. And like I already kind of spoiled my surprise, I would like to leverage, I call this the onion model of testing, right? Developers rely on testing heavily in order to ensure the quality of their software. They use unit testing to test functions, integration testing to test other bits, and functional testing to test other components as well. We have to actually start including security and governance as a part of this standard test suite. Those very same tests that developers already run day to day as a part of their software development pipeline, we have to start including security aspects of there. Security has such a wonderful tool set like Metasploit or other things that can already be leveraged and exploited as a part of this. And from a third-party dependency point of view, we can actually make them run as exactly like normal tests. So here I have a failed Maven build that is failed because there is a test that fails because Commons file upload has a known security vulnerability. So you cannot even run your build because the security vulnerability already exists. This is much faster feedback for the developer than just, you know, waiting until the system is already being deployed. We can run these sorts of tests very, very easily as a part of, you know, every sort of continuous integration pipeline. There is still need for more slower human-led analysis as well. You know, that doesn't mean that you shouldn't, you know, do things at various different times. But what it really means is that we need to find a place for these sorts of easy coverage types of tests, these sorts of synchronous tests that I call them, that give you just enough information in order to action it as a part of your development, and then run deeper dive analyses outside of the development process. But already, by doing these sort of basic tests where, you know, where you ensure that, you know, all of these kind of basic CVEs are out, you're mitigating a lot of risk and a lot of security problems in the first place. So this can give rise to what I call the rugged software factory, meaning we can leverage the very same tools that already existed there in order to then leverage that build stage to run, you know, these dependency analyses or this kind of on-the-go quick checks of what's happening with the third-party components, and then run a larger static analysis later on in the delivery cycle. And what that gives us is early feedback about these things, allows us to give a control point that is within our control, and doesn't allow developers to, you know, put on a hotspot and subvert some of the measures that you've done, or doesn't allow them to just tick a box in the checklist, but actually that is something that is within your control. And finally gives you trusted objects that you can then deploy. The final thing I'm mentioning today is the bill of materials, which is a list of all of the components that go into your application. And the very simple reason why you want this is because one of the most common ways of facilitating security, especially in companies that don't have a security person, is that these articles get forwarded, sent up, you know, one guy sees it, sends it to his colleague, that gets forwarded to another guy, that gets forwarded to his boss, gets forwarded to the CTO, and suddenly the entire company is scrambling to reverse engineer everything they've ever deployed for over the 10 years to figure out if something is actually in production. Instead, you should collate, if you're already testing for these dependencies, you should collate a bill of materials, a list of ingredients that went into building that specific release. What were the components that we used in order to build that release? Because car manufacturers, when they pull out a car out of the factory, that car has a list of ingredients, so that if one of the components fails, then in that case, you know, they can issue a pullback instead of, you know, reverse engineering every shipped car out there in the field. So ask yourself, do you want to do a manual reverse engineering operation, or do you just want a database to search against? I think it's quite a simple answer, really, isn't it? And finally, one final thing that I want to do, because we're running out of time, is that leadership is important. To me, as a developer, the security guy has always been this guy. It's been that troll under the bridge that sits just on the bridge to you know, the green future in tomorrow that I want to where I want to ship my application. Comes from on the bridge and says, "FIFO, you gotta do a pen test, bro, before it's actually allowed there." Like I said, instead of working against the development teams, we should, one of the greatest ways of instigating leadership and understanding of security is actually to build knowledge in terms that the developers and the operators understand. In my case, the most effective thing that I've ever seen is including it as a part of their everyday testing cycle, making sure that the security enables and doesn't block the process. The assertion that I'm making is that, you know, if you look at historically about how different functions in software development have gone, testing has become test-driven development. We are now writing tests in order to develop code. Usability testing, you know, clicking on the user interface, has become behavioral-driven development. We have cucumber tests, we have other tests that allow us to run usability and user interface testing automatically. Integration testing, running a system in a production-like environment, has become model-driven development with by leveraging things like Chef or Puppet or other configuration management tools. And now, in fact, probably container-based development, because we can now have a unified environment across all of the targets. So QED, in this sort of way, security has to become a part of the development. We have to start facilitating security-driven development. Write tests first, test against for every build, and then ship if tests are compliant. And also, you know, be transparent with knowledge. So in conclusion, you know, if you do use tools in the right way, what you can facilitate is a rugged software factory that can facilitate these sorts of things, that can really help you make the security as a part of that process, make the developers actually ship faster, not slower, because of security considerations, blah, blah, blah. We have these 5 things. They have loads of benefits. And really, if you look at the aspects of security, these can be chalked off very, very nicely by using these sorts of methods of way. And finally, for change, doing the right thing is actually also doing the cheapest thing. You know, mitigating problems earlier on and allowing the developers to issue fixes to their own code helps them fix problems faster and also cheaper, because, you know, less time in development, less time remediating issues, and less time creating value is less time, you know, generating revenue. That's it. Thank you very much for listening, everybody. I hope you got something out of there. So here are all of my references. You'll see them in the slide deck that will be shared later on as well. Do have a read of all of the reports, because they're very interesting data. Thanks. That's a very, very, very good question. The question was, if I have a multiple language environment, how do we scale this up? So how can we scale this this sort of way of working, not to just only apply to one single piece of the puzzle, but also to other places. That's essentially what we were asking. The answer is there are vendors out there. I might work for one, but there are vendors out there that do supply products that actually contain support for more than just one language. So ideally, what you want to think about is actually more of a system that can support many of these things. I mean, each vendor, each programming language, for example, and supplier and system do have their own artifact repositories. So you might just want to look at, having, one of each. But there are also combination solutions that allow you to actually aggregate all of them into one single server. In my experience, that's more effective, in my practitioner experience as well, is, do you want to manage 15 different servers for 15 different languages or just one? Does that answer the question? Okay?
Thank you very much.
Thank you very much.